In this video, we're going to be talking about some of the design of experiments basics, including some basic terminology, some of the different types of situations that we can deal with, some of the different topics that we'll be talking about, and some major ideological concepts that will be important for us to distinguish between as we go on in this experimental design process. We'll end this video with a quick example before moving on to how to implement your own experiments, which will be important for your first project. So some basic terms are a good place to start, and you'll hear of these types of terms throughout the course. The first distinction is between mechanistic, if you can say that word, mechanistic, and empirical models. Now, I think of this as the difference between mathematical and statistical modeling, though that's not quite fair to say. Mechanistic models are models that are determined by, say, an equation. So in a mechanistic model, think about the conversion between Fahrenheit and Celsius. Celsius is the degrees in Fahrenheit minus 32 times 5/9. And that's always true. If you have a degrees in Fahrenheit and you apply that particular formula, you will always, with perfect precision, get the exact degrees in Celsius. There is no variation. If I go to Australia and I do that, if I do that in the United States, if I do that in the South versus the North, or in the East versus the West, it doesn't matter. That relationship is always true. So mechanistic relationships are very useful principles for things like physics when we're measuring the nature of something. But in social research, it's not quite that simple. And frankly, even in many hard sciences, medicine, it's not quite that simple. As you get taller, do you get heavier? Well, yeah, you tend to. But are taller people always heavier than shorter people? Well, no, that's not always true. It really depends on the person and the situation. So in that particular case, that's what we call an empirical model. It's a model where you can consider a relationship and determine the nature of a relationship, but it doesn't always work out the way you think it will. So in an empirical model, you may have something like, I don't know, the relationship between weight versus height, and as your height increases, your weight tends to increase, but that's not true for everyone. So if I come up with an average relationship, and that's what we do in statistics, is we look for average relationships between your weight and height, an empirical model is going to be wrong if I try to use your weight to predict, or excuse me, your height to predict your weight. That doesn't quite work like that. So it's important to be aware of both the mechanistic and empirical models. Mechanistic models tend to be more like physics, like a physical outcome, or again, you can think of theoretical mathematics. Whereas empirical outcomes tend to be much more driven by data instead of theory, where in the data we can see that not everybody perfectly applies to a particular formula or equation. And frankly, that's what the art of statistics is purely studying, is these empirical models more than the mechanistic models, which is again why I sometimes look at these as the distinction between mathematical and statistical modeling, though mathematical modeling is more flexible than just mechanistic models. Another important distinction is between factors and levels, and this is a very, very, very important one to take lots of notes on, because the distinction between factors and factor levels is something that we will use for the rest of class in probably every video that we have from now on, so it's really important that you get this distinction. A factor is a categorical variable. So you can think of your favorite pizza topping. You can think of someone's gender or sex. You can think of a person's hair color. You can think of somebody's favorite superhero. It's a variable that can have a variety of different answers and tends to be categorical. Do factors always have to be categorical? For this class, we'll say that factors are always going to be categorical. Though to be quite frank with you, I think that just tends to be a tendency. I'm not sure if there's a theoretical rule that has to be the case. But it does have a tendency. Actually, I should mention here that factors sometimes are continuous but split into categories. So let's say I'm doing an experiment where I want to look at what happens when I'm baking cookies and I bake them at different temperatures. So let's say I want to bake them at 200 degrees, 300 degrees, and 400 degrees for 10 minutes and figure out which one gives me a better cookie. Hey, that might be a great first experiment that you could consider doing on your own. Actually, that's very similar to the very first experiment I ever did when I took a very similar class to the one that we're going to years and years ago. So in that particular case, though temperature of the oven is truly a continuous variable, you could set it to anything, literally any number, right, within a certain range. But you could certainly have half degrees and quarter degrees, so it's a true continuous variable. It's being treated as a categorical variable because I'm only looking at three categories. I'm looking at 200 degrees, 300 degrees, and 400 degrees, and you can split those into three groups. So that particular variable could absolutely be counted as a factor, and it's because I'm looking at it categorically. So that's what factor is. It's kind of like a variable, and again, it's a variable that we're treating categorically. The level of a factor is what are the options that the categorical variable could have. So in that cooking example, the factor is temperature, and the level of the factor is 200 degrees, 300 degrees, and 400 degrees. It's all of the options that I could have. Those are my factor levels, or all of the options that I'm going to use for my experiment. So let's say we were looking at hair color. So hair color would be the factor, and then the levels of that factor would be what? Brown, blonde, red, and black. So there's 4 levels of that particular factor. I guess we could do like purple and blue, but whatever ones we'd have in our experiment are the ones that we would focus on. So we have the factor, hair color, and the level. What are the different, like what are the different results? If you went and asked somebody, what's your hair color? Hair color would be the factor. That's what you're asking about. And then the result, well, that would be the different levels. The levels are the different options that it could take. Experimental units. Now, this is important to realize. When we run experiments, what are we running experiments on? So in the particular oven example that I mentioned, what am I actually doing the experiment on? Well, I'd be doing the experiment on little raw pieces of cookie dough. So I'd be experimenting on individual chunks of cookies. Sometimes you run your experiments on people. Sometimes you run your experiments on a system, like a school. I'm going to do something with one school and something with another school. It's important to excuse me. It's important to realize with experimental design that experimental units are literally what are you running your experiment on? How are you breaking down the groups? And it's important to be able to acknowledge, well, what am I running my experiment on? Sometimes this can also be subdivided into a different couple categories where they add a definition called a measurement unit. So sometimes you can do experiments on things that you're not measuring. So let's say I wanted to implement policy A at a school and policy B at a different school, and I wanted to see how it impacted student test scores. Well, my experimental unit is the different schools, but what I'd be measuring in terms of test score wouldn't necessarily be the school, it'd be the student. And sometimes we can have some different designs that take into account that. But typically in the course, I'm going to treat our experimental units and measurement units similarly so that we don't dive into that. And I will tend to call them experimental units or just, components in the sample. All right, controllable versus uncontrollable variables. Now, this is also an important distinction, and we discussed this with the process briefly earlier, where we looked at the input and the output, and we had controllable and uncontrollable variables. So controllable variables are literally things you can control. So if you want to think about something as a controllable variable, it would be something where you have control over that particular thing and can change it if you wanted to. So for instance, I have control over what curriculum students are taught in my courses. And if I'm cooperating with teachers, I have control over what curriculum they are teaching. So I can control the different types of curriculum that are being used in different courses. Now, what could I not control? Well, maybe I couldn't control um, something like the weather outside. And so for an uncontrollable variable, that's something that we actually don't like in our experiments. Now, I should say for control, it's kind of an interesting thing here because sometimes what I can do is I can control in the experiment an uncontrollable variable in general. So take something like a person's sex. A person's sex, I can't just go around and assign somebody to be male or somebody to be female or another sex. I would have to, that's just not a reasonable possibility or an ethical possibility. But what I could do is when I'm splitting, say, some different groups up, I could control how many males are in a particular group and how many females are in a particular group. So in a sense, though the variable isn't controllable per experimental unit, I may have some control over it. So it's important to realize that when we talk about controllable and uncontrollable variables, it kind of depends on the context. Now there's a couple ways that we talk about these variables. First of all, if I can control the variable and I care. So this would be a case where I'm looking at the different kinds of pedagogies that I can do, and I can control what I teach in a particular class, and let's say I care about that, that's what I want to study, then this is something that we call an IV, or an independent variable. And again, this might be true for boys and girls too, though I couldn't take a person and assign them to be in the male or female or any other groups I wanted to use. Then though that's not a possibility, I may be able to say, well, I can look at the difference between those individuals anyway. So it's important to realize that controllable and uncontrollable in this particular case is an independent variable. It really depends on the experimental design. So if I can control but don't care, so let's say I'm implementing pedagogy and I want to be able to account for the fact that maybe guys and girls have different responses to this particular new teaching style, but I don't really care about that. I just want to be able to control for that. Then something that we could use is a statistical technique and an experimental design technique called blocking, and we will have an extended discussion about this later in the course. If it's a variable that I can't control, so let's say the weather, or let's say a person's starting IQ, that's not something I can look at a person and just change in a course. Then what I might do is I might use a covariate in the model to account for that source of variation that I can't control. And when we use a covariate in a model that involves primarily categorical variables, sometimes it's called an ANCOVA. Now there's also uncontrollable variables that I can't control, or even controllable variables that I haven't thought about. And this happens all the time. I think one of the biggest mistakes of young researchers is to think that we have way more control than we actually do. And in truth, there's a ton of variables that we have no idea if they're out there. Now, one trick that we take advantage of is the concept of randomization, where we randomize our experimental units into their groups. And what that does, if you think about it, is if, let's say, all of the people, all of the experimental units come from kind of the same cluster or group or population of experimental units, if I just kind of randomly assign them to the groups, hopefully that randomly evens out the levels of the uncontrollable variables in all the different groups. Now, if I know and can control it, then I can block them in and make sure that there's an equal amount of males and females into each group, let's say. But let's say there's a variable that I didn't think about. Let's say hair color was really important and I didn't think about that. Then hopefully randomization, randomly assigning individuals into each of the groups, is really going to take advantage of this. Now make a note real quick here on your notes that this is a random assignment, not random order, and we'll talk about the difference in a moment. Now there's one other thing I should mention here. I think you'll notice through the course that in design of experiments, we tend to use a statistical analysis called ANOVA, which stands for Analysis of Variance, and we'll talk about that more later. And we use that much more than we do regression. The reason is because when we're looking at our independent variables, we tend to have control over them. And if we have control over them, typically we set them to a fixed number of levels. So think about the temperature I was baking cookies at earlier in an earlier example. I have control over that particular temperature. So I'm not just going to spin the knob and pick a variety of random different temperatures to bake cookies at. I tend to select a variety of different temperatures and then replicate at each of these different temperatures. 200 degrees, 300 degrees, 400 degrees is what I mentioned earlier. Then I could pick some in the middle if I wanted to get a little bit more precision with that particular estimate. So when I can control the variable, and in experimental design, I'm assuming I can control the independent variable. I tend to assign it a fixed number of levels. And because of that, I tend to have a categorical independent variable. And that's why far, far, far more often than regression in design of experiments, we use ANOVA. Now, response surface methodologies, again, that's later in the textbook, and we make it there at the end of the semester. That's a bit of an exception from this rule. But by and large, when we have control, we tend to pick a fixed number of levels, and then our independent variable tends to be categorical, not continuous. All right. So, observational versus experimental design. Now, this is a big, big, big piece of what we talk about when we talk through design of experiments. In an observational design, we are assuming that I do not have control of the independent variable, that the independent variable I'm trying to study is something that I don't have control over. In an experimental design, we assume that I have control over the independent variable and thus can randomly assign experimental units to that independent variable and to not have that independent variable. Observational studies lead to correlational claims. Experimental studies are largely thought to lead to causal claims, and we'll discuss this a little later. The truth is a little more subtle, that observational studies do lead to correlational claims. Experimental studies are necessary but not sufficient to lead to causal claims, and what that means is it's a step on the right path, but just having an experimental study doesn't guarantee that your claims can then be causal. So I mentioned this idea of randomization for both assignment and order, and the concept is actually not particularly complicated. Randomized order means running the trials in a specific order. And that's really all it is. If I'm going to, say, have 15 experimental units, well, which one do I use first? Now, random assignment assigns the experimental units to random groups, or I should really say random factor levels, now that we've discussed what a factor and factor level mean. So we're assigning the experimental units randomly to the factor levels in the independent variable, and then we'll see how blocking is a restriction on randomization when we get to that point in the course. Now, the benefit of this, as we discussed on the previous slide, is this balance out the effect of lurking variables, or those unknown variables that we can't control for. So in that particular case, the random assignment of these experimental units allows us to say with reasonable confidence, we don't think another variable is the cause of the relationship that we're seeing within the experiment. And that's why an experimental design is necessary for causal claims. Now, ultimately, in causality, we have to deal with a concept called internal validity. And internal validity is just the concept of how much do we trust that the results mean what we think they mean. So let's say I randomly assigned a temperature to different cookies and saw that the cookies that were cooked at 300 degrees for 10 minutes came out better than the cookies that were cooked at 200 degrees or 400 degrees. Does that mean that if I cook cookies at 300 degrees, they come out better? Well, that's the concept of internal validity. Does the experiment results mean what you think they mean? There's a variety of different threats to internal validity that we can have. There's selection bias, there's the researcher threat, there's the history And there's a whole ton more that you can look up. I'll say that when we utilize the experimental design, what we balance out is the selection threat to internal validity. So we're only taking care of one of these, and this is why I would consider experimental design to be a necessary but not necessarily sufficient key in order to make causal claims. All right. So there's a couple of basic principles in design of experiments. We've talked a lot about some terminology, but two basic principles. The first one is replication. Now, replication is kind of what we mean when you think of sample size. And really what it is how many times did you repeat the experiment, or how many experimental units did you use in order to repeat the experiment. Now, the higher the sample size, the more precise estimates that we can have of the particular effect, and the better we can estimate the background noise. So as the sample size increases, the size of the background noise decreases, and what you can think about is as I get more and more evidence in something like a court case, it becomes more and more clear if somebody's innocent or guilty. Now, replication is very distinct from a concept called repeated measurements, and you can check your textbook for more details here. Replication is the number of distinct experimental units that I have in an experiment. Repeated measures is the idea of taking an experimental unit and measuring it multiple times. So let's say I had 10 students on a sports team, and I wanted to look at the number of jumping jacks they could do, the number of squats, and the number of sit-ups that they could do. What I may do is, instead of assigning 3 to jumping jacks, 3 to squats, and 3 to sit-ups, I might have each person on the sports team do all 3 of the exercises. Now that breaks our normal statistical methods, because the results of the squats may be related to the results of the jumping jacks, which may then also be related to the results of the sit-ups. So what does that mean? What that means is more fit people may be able to do more of all of the exercises, and less fit people may have more struggles with the rest of the exercises. And that needs to be accounted for, because under normal statistics, we assume that all of the observations are independent. So the concept of replication would be like adding more players to that study, whereas the concept of repeated measurements is the idea that instead of grouping a group of players into squats, grouping a group of players into sit-ups, etc., we actually repeat measurements on each experimental unit or on each player on the team. A second very large and important concept in design of experiments is the concept of blocking. Now, we mentioned earlier, but blocking is the primary way in which we deal with nuisance factors that we can control. It is a really important methodology that we take advantage of, and it's not just a statistical methodology that we can use, it's actually built into the core design of the experiment. It's a fantastic way that if we have main nuisance factors that are knowable and controllable, but that aren't the factor that we're intending to study, that we can really completely remove them from the design of experiments. It's a very, very, very cool technique. And we're going to spend a great deal of time focusing on this later in the course, so I don't want to take too much of our time here on it. But it is one of the basic principles of design of experiments. So we use replication, and the whole purpose of replication, by the way, is to get a really good estimate of the error noise and to account for that. Blocking identifies variables that we don't want to include in our analysis, and through designing the experiment appropriately, removes them from consideration in the outcome so that we can just focus on our variable of interest. In this video, we've discussed quite a bit on terminology and some of the background concepts that'll be important in designing experiments. In the next video, we'll go into a brief example of designing experimentation before we close out this lecture set with a discussion of the steps of designing an experiment.